Dear all, I am Dr. B. Malati, Associate Professor, Department of ECE, SR University, Warangal. In this video lecture, I am going to simulate biopotential amplifier for biomedical applications. We have to create a small ECG-like signal, and then we have to add random noise and 50 Hz power line interference. Then we have to amplify the weak signal to filter it using a band pass filter. It will display the raw input signal and then corresponding output signal. So I have written the code in Python and I will simulate in the Google Colab platform. Now I am going to share the screen. So after simulation, we get the input biopotential signal in millivolt range, and it is a graph of time in second versus voltage in V. It is amplitude of the envelope. And then after instrumentation amplifier, what is the signal? It is the waveform of time in second versus voltage in V. Then filtered output signal time in second versus voltage in amplitude. So now I am going to explain line by line. So first one, what this code does. This imports the NumPy library and gives it the short name NP. So NP is the NumPy. And the NumPy is used for numerical calculations, arrays, sine waves and random values. This imports matplotlib plotting module and gives the short name PLT, and it is used to draw the graphs. This imports two functions from scipy.signal. So first one, butter. It is used to design a butterworth filter. Then filter. It is used to apply the filter without phase distortion, no time delay. And this sets the sampling frequency to 1000 Hertz. This means the signal is sampled 1000 times per second, and Fs is sampling frequency. Hertz samples per second. This creates a time array from 0 to 1 second with 1000 points. So, time contains time values like 0.000, comma 0.001, then 0.002 up to 1, and this is used as x-axis when plotting the signal, and then it tells us that the next line create a simulated ECG like signal with low amplitude. So what it does? This creates ECG signal. So previously import library from modules, and Fs is equal to 1000 in Hertz, and T is equal to NP dot linspace open bracket 0 up to 1. So this interval is divided by Fs. So 1000. So this 1 by 1000 is equal to 0.001. 1. Simulated ECG signal, ECG underscore signal, it is equal to 1 e power minus 3 into NP dot sine 2 pi 2t. So normally this signal is sinusoidal waveform, so that we have to write in terms of sine, and sine omega t. So omega means it is angular frequency conversion to pi f. Here f is frequency and ECG signal frequency is a very low frequency, that is why 2. And then normally sinusoidal representation is A sine omega t. So A is the amplitude. Here 1 into e power minus 3. That is 1 into 10 power minus 3. That is equal to 0.001. This is 2 hertz. That okay, that I told you. Then a sine function, it creates a sine wave. So this signal is a sine wave and frequency is 2 cycles per second. Then amplitude 0.001 volt means it is 1 millivolt. This represents a small biopotential signal like ECG, and this creates a random noise. And what is this noise is equal to 0.3 e power minus 3 into NP dot random dot RANDN, that is random number, and open bracket LEN open bracket T. So power line is equal to 0.5 e power minus 3 into NP dot sine open bracket 2 into NP dot pi into 50 into T. Now we have to add the noise. Now we will break down. So sine wave with frequency 50 hertz. And then amplitude is 0.5 e power minus 3. That is 0.5 into 10 power minus 3. So 0.0005. That is equal to 0.5 millivolt. That is 50 hertz. Our power line, that is 230 volt AC 50 hertz. That is why 50 hertz. Then you can ask why 50 hertz power supply is taken here, because if we install 2 electrodes around the heart muscle, then electrons will flow towards or repel. So the ions, the movement of the ions will contribute to the current. So it is the electrical signal. That is why 50 hertz we are taking into account. Then noise is equal to amplitude is 0.3. So when compared to the original ECG signal, we have to take the small magnitude of noise, because it should not overcome the original signal. But noise is a high frequency component only. That is why the frequency is more for amplitude when compared to the ECG signal. Now, noise is equal to 0.3 e power minus 3 and NP random dot. So, random noise, the type of the random noise is white Gaussian noise. It is taken as reference and the random numbers are generated. So, LEN open bracket T. So, the time axis is same what we have used for the ECG signal, because whatever the processes are applied on ECG, the same thing will be applicable to the noise also. That is why the time length of the time should be same and uniform for both the cases. So, if the sampling frequency is 1000 hertz, Same thing is suitable, applicable for the noise also. So both are common. Only thing frequency is different. Frequency is more for noise. Otherwise, whatever the processes we are applying to ECG, the same thing is applied on the noise also. So next one. Next one, input signal is equal to ECG underscore signal plus noise plus power line. So finally, we cannot give the raw input signal. We can give, but automatically from the environment, the noise will be getting added to the ECG signal before given to any process. In the same way, while taking also, it will be added with the power line interference. So when we are taking, automatically the waveform will be having the power line interference as well as noise. So for the process we have to include this. There is no raw input signal. So input signal is equal to ECG signal plus noise plus power line, and then gain is equal to 1000. So high cut is equal to 40, order is equal to 4. So finally we are getting the raw contaminated signal, that is input signal is contaminated signal. Contamination done by the contamination happened by the inclusion of the noise and power line interference. Now why we get 1000? This sets the amplifier gain to 1000, and this means the signal voltage will be multiplied by 1000. So amplified signal is equal to gain into input underscore signal. So we know that gain of any amplifier is equal to output by input. Output is equal to input into gain, and here we are taking the low cut is equal, it is low pass filter type we are taking. So low pass filter means sorry, a band pass filter we are taking into account. So band pass filter means it will be having two frequencies, lower cutoff frequency and then higher cutoff frequency. So the frequency components below the lower cutoff frequency will be removed, and the frequency components higher than the higher cutoff frequency will also be removed. So both are called as stop band, and the frequencies in between, lying in between 0.5 to 40 Hz, they will be allowed to enter into the pass band, pass filter. So they are called as pass band. And then above 40 Hz, why we are not considering? Actually high frequency is for noise. That is why they are assumed to be as noise components, so that they have to be removed. And then order is equal to 4. So the order of filter, the higher order filter we are taking into consideration. Normally 1 is nothing and 2, 3 automatically higher order, but still 4 if we take, it is expensive, but at the same time the filtering will be very steep filtering, very high filter action will be happened. That is why higher order filter, that is fourth order filter, we are going to take here. And then B comma A. So here using the gain, we have to, I am giving more explanation. If the original signal is very small, amplification makes it easier to process and analyze. So why we already I told you that the ECG signal is of low in magnitude, it is not strong. So after processing, still it will become, if it is becoming weak, then it will not be possible possible to recognize the signal. That is why before processing we have to give some amplification. Then it will be easy to detect. For example, suppose 0.001. So it is in millivolt. So it after amplification, suppose if it is multiplied by 1000, we will get 1 volt. So in this way, millivolt range is converted into 1 volt. So this simulates the instrumentation amplifier. Then low cut is equal to 0.5. So this sets the lower cutoff frequency to 0.5. Frequencies below 0.5 will be reduced, that is removed, and this helps remove very low baseline drift. And then high cut is equal to 40. So this sets the upper cutoff frequency is equal to 40 Hertz. Frequencies above 20 Hertz, above 40 Hertz will be removed. This helps remove high frequency noise. And then order is equal to 4. This sets filter order to 4. The higher order filter gives sharper filtering but may be more complex, that is computation will become complex. And then b comma a, it is equal to butter open bracket order comma low cut divided by fs by 2, and then high cut divided by fs by 2 by b. B type is equal to band. So what is the meaning? Filtering means we have to generate the filter coefficients. They are applying on the input signal. So B is the numerator of the filter coefficient. A is the denominator of the filter coefficient. Then butter worth filter. We are applying, that is order is fourth order. So low cut is equal to 0.5, low cut of frequency we know, divided by fs is equal to, already we know it is 1000 by 2 it is 500. So 0.5 by 500. In the same way, high cut is equal to 40. So 40 by 500. And B type is equal to Butterworth filter type is equal to band pass filter. And why we are doing Fs by 2, dividing Fs by 2, dividing Fs by 2. So the cutoff frequencies should be normalized. So if they normalize, that value will become will be ranging from 0 to 1. So the values will be lying in the 0 to 1 only. Beyond that it won't go. That is why normalization of the cutoff frequencies is necessary. Actually, we are applying sampling. So, sampling means we are going to convert from the analog to digital. Next one, in this way, it becomes a Butterworth band pass filter. So, why Butterworth filter we are adopting? It creates filter coefficient smoothly and order is equal to 4, and then using normally Fs by 2 is nothing but Nyquist frequency. So Nyquist criteria should be fulfilled when we are sampling. What is the meaning? Suppose Nyquist criteria is sampling frequency should be greater than or equal to maximum frequency content present in the waveform divided to twice the maximum frequency content present in the waveform. So if suppose the Nyquist criteria is not fulfilled and sampling frequency is less than 2 into maximum frequency content present in the signal, then what will happen? The lower frequency, because Fs is less than I told no, so This will make the low frequency content to resemble as the high frequency content. So it is called the aliasing. So similar to that is why it is aliasing. So this aliasing is the undesirable one, so that it should be avoided, and it is it is overcome by using the anti-aliasing filter. So after normalization, what we will get 0.5 by 500, which is equal to 0.001. Similarly, 40 by 500, which is equal to 0.08. So B type band means it is a band pass filter allowing frequencies between 0.5 Hz and 40 Hz. So B and A are filter coefficients used later. And then filtered underscore signal. It is equal to filter open bracket B comma A amplified underscore signal. So now what is the meaning? This applies the filter to the amplified signal. So B comma E are filter coefficients. Amplified signal is the signal being filtered. Then filter applies the filter in the forward and backward direction. So filter means two times the filtering operation is performed in the forward as well as backward, so that very smooth filtering action will be done. So noise is reduced and phase distortion is minimized. No time delay. So for these features we are using filter. This gives a cleaner output signal. And then we have to plot the figure. So PLT dot figure open bracket figure size is equal to 12 comma 8. So this creates a figure window for plotting. Width 12 inches and height is 8 inches. Then plot dot PLT dot subplot 3 comma 1 comma 1. This divides the figure into 3 rows and 1 column and selects the first spot. So there will be 3 stacked graphs, and then PLT dot PLOT open bracket T comma input underscore signal. This plots the input signal versus time. So input signal is represented as an envelope. Envelope means the amplitude in voltage. So x-axis is equal to time. Y-axis is equal to input underscore signal. And the title given to it is Input Biopotential Signal. It is millivolt in range. So this gives the first graph. And then PLT dot Y label. It is voltage. So this labels the Y axis as voltage. And then PLT dot subplot open bracket 3 comma 1 comma 2. This selects the second subplot, and then PLT dot PLOT open bracket time comma amplified underscore signal. This plots the amplified signal versus time. Once again, time is exact. Amplified signal is anyway electrical signal envelope only. So voltage we will mention in y-axis. And we are giving the title after instrumentation amplifier. So Y label is mentioned as voltage in V, and X is as usual time. Then plot dot subplot 3 comma 1 comma 3. So this selects the third subplot. So third subplot. PLT dot PLOT open bracket time comma filtered signal. So this filtered signal is nothing but the waveform only. So the amplitude is mentioned in terms of voltage. And PLT dot title. The title filtered output signal is given, and then X label. So X label we know it is time in second. Y label voltage, amplitude voltage. And then PLT dot tight underscore layout. So this automatically adjusts spacing between plots, so labels and titles do not overlap. So tightly fit all graphs are fit uniformly. The distance will be uniform, and then PLT dot show. This displays all the plots. So what we are getting input biopotential signal millivolt range. So x-axis time and y-axis voltage. And then instrumentation amplifier x-axis y-axis. See here it is the amplitude positive peak and negative peak. If you take it is 0.002 only, but instrumentation amplifier is gain is 200. That is why it is the amplitude is 2. So here 0.002 only, but after amplification the signal will become higher, but the time in second it won't change. So after filtration, so here we will get the spikes in and around the waveform, in positive as well as negative, but filtered output signal will give you a smooth waveform without any spikes. So it is also drawn time in second in x-axis versus voltage in volt. So the amplitude is voltage. So what the full code does? This program simulates a biopotential signal processing system, and it creates a small ECG-like signal. So it adds random noise and 50 Hz power line interference automatically before being applied to the processings. So and then it is added with the random noise and 50 Hz power line interference. Then it is amplified. So the weak signal, still it is weak signal, it is amplified. And then filtering is applied using band pass filter. See, finally it will display raw input signal and then amplified signal and then filtered signal. See, in simple words, it shows how a weak biomedical signal is. It is captured and then corrupted by noise, then amplified, then cleaned using filtering. This is very useful in ECG, EEG, EMG and other biomedical instrumentation systems. So, one line summary of each stage. ECG underscore signal. It gives the original weak signal. Then noise. It will give random unwanted signal. And then power line. It will give 50 Hz interference. Input underscore signal. Therefore, it will become a noisy input signal. Then amplified underscore signal. It will become a boosted signal. Then filtered underscore signal. It will be the clean output signal. So in this way, we got, so first one we have to import the NumPy, that is Python, from the module. So in the second, next one we have to import matplotlib, that is library functions. They are imported from the pyplot module. So then scientific dot signal. So it is import, and what is the meaning? Signal is the module and SciP is the library. So from the module library is imported, but the signal contains many functions, out of which we are using butter comma filt. Only two functions are necessary for this program. That is why these two functions are imported from the signal module. And then sampling frequency, we know it is 1000. Number of samples taken per second. So, the time axis starting from 0 and ending at 1. This 0 to 1 is divided into so many parts based on the sampling frequency. Equal and uniform space between time interval between any 2 points. But if the time interval between the 2 points is very low, then filtering action will be very smooth. In the same way, the sampling frequency will be taken as more. So more samples, so more time interval between the two extreme edges starting from 0 and 1. So we have learned the biopotential amplifier simulation for the biomedical applications. We have taken the ECG signal as an example. So with this we conclude. Thank you.